Welcome back to Precalculus. We're in Chapter 8, Section 2 now, discussing three variable systems. So let's just dive right in and get to some vocab. Just a quick review, the solution to an equation in one variable is a single number that satisfies the equation, and the graph is a point on a one-dimensional graph. The solution to an equation in two variables is an ordered pair that satisfies the equation, and the graph is a line on a two-dimensional graph. The solutions to an equation in three variables are an ordered triple, which we will visit later, that satisfies the equation, and the result is a plane in space in a three-dimensional graph. So you can see right here we have an example of a three-dimensional graph, and we're being asked to plot the point 5, 3, 4. Okay, so that means just like in our two-dimensional graphs, when we move parallel to the x-axis and y-axis, we're going to just now be adding in the added effect of moving parallel to the z-axis. Our 5 will be our x, our 3 will be our y, and our 4 will be our z. Okay, so quick note, the axes are oriented a little differently than maybe we're used to here, but that's okay. We're still applying the same concepts. So to plot 5, 3, 4, we're moving parallel to the x-axis, 5 units. So 1, 2, 3, 4, 5, right there. We're going to move parallel to the y-axis, which will be the same length as here, but it'll be off the end of our already moved x variable. So about right here, 3 units, and then 4 units parallel to the z-axis, so vertically up 4 as it's oriented currently. 1, 2, 3, 4, about this length right here. So our result point is about right there. Okay, the point 5, 3, 4. Now we're being asked to find a solution. There's multiple solutions to the equation 3x minus 2y plus z equals 6. Anything as simple as the point 2, 0, 0 is a solution to this equation because 3 times 2 is 6, minus 0 plus 0 is 6. Or the point 0, 1, 8 is also a solution because 0 minus 2 plus 8 is 6. One more is the point 2, 2, 4 because 6 minus 4 is 2 plus 4 is 6. So all three of these ordered triples are on the plane that is a solution to this equation. So each equation in a system of three equations with three variables represents a plane in space. Now you can see my drawings here that I've got of each different one. I'm going to give these guys a name and a vocab so we can all speak the same language. So if we have a unique solution, we have exactly one solution, and you can see we have three planes intersecting at exactly one point. If we have linear dependence, we have infinitely many solutions. And you can see we have three planes kind of intersecting, kind of like a pinwheel sort of thing, and they intersect to form a straight line. I can put it in red here for you. Red and black, I guess. If we have coincidence dependence, we have essentially three planes that are all the same equation, meaning they're laying on top of each other. So each plane is essentially a different scale factor of itself, and it intersects at all points. And if we have no solution, then we have no solutions, zero solutions, and we have essentially three planes that never intersect all planes at the same time, kind of like this, but they never intersect. They may intersect two, maybe intersecting, but they never intersect third. Another way of thinking about this is if you have three parallel planes that are all parallel to each other, they will never intersect. Therefore, there will be no solution. So let's dive right in. Let's get some examples going. Real sorry, my marker bled through my paper there. But let's solve a three-variable system. Notice we have three variables we're solving for, so we are going to need three equal signs, three equations, three planes. If we can solve for it, it's going to be a unique solution. That means those three planes intersect all at one point. So we're going to use the process of elimination here. Okay, so the first variable that I'm going to attack to try to eliminate here is going to be the x variable. I'm sorry, I'm not going to attack the x variable. I'm tempted to attack the x variable, but I notice if I add together line 1 and line 2, that I'll simply be putting a z variable into my equation, thus getting me nowhere. So I'm going to attack my z variable, which means I'm going to need to multiply my top equation by 5 and my bottom equation by -3. So let's go ahead and do that. So that gives us 5x minus 10y plus 15z is equal to 45. And if I'm going to be adding it to my bottom equation, that's going to give me -6x plus 15y minus 15z. You see my z's are getting ready to cancel out as soon as I add my two lines together. And 17 times 3, -3 is -51. So now if I add together these two planes, these two equations, I get -x plus 5y, my z's cancel out, is equal to -6. Now if I take that and I add it to my second equation here, -x plus 3y plus, is equal to -4, I'm not going to get anything to cancel out. But I need to find another way to eliminate another variable. So what I'm going to do is I'm going to take this second equation and I'm going to multiply it by -1. So that when I add it to my new equation, I get my x's to disappear. So I'm going to rewrite my new equation, -x plus 5y is equal to -6. And now multiplying this middle equation by -1, I get x minus 3y equals 4. Let's add them together. X's cancel out. 2y is equal to -2, meaning y is equal to -1. Okay, now that I have y equal to -1, I can take it back and plug it into any of my equations that only have an x and a y or a z and a y, because I only want to have one variable to solve for. I'm just going to take it back, plug it into my new equation over here, and I'm going to have -x plus 5 times -1 is equal to -6. So -x minus 5 is equal to -6. I'll add my 5 over. -x is equal to -1. So x is equal to 1. Now that I have an x and a y, it's just a matter of plugging it into an equation that has a z in it so that I can solve for z. Let's just choose the top equation. So that'll mean 1 minus 2 times -1 plus 3z is equal to 9. So 1 minus -2, that's 3, plus 3z is equal to 9. 3z is equal to 6. Z is equal to 2. So my solution to this system in three variables is the ordered triple 1, -1, 2. Okay, jumping down, we're going to apply the same concepts of elimination and try to solve a system that we're going to find out here is inconsistent or dependent here. So let's pick a variable to attack in this system here. All of them have all three variables in each line, so we're free to go after whatever one we want. Right now it's looking like, oh, I can add together these two and get my y to disappear very quickly. Okay, so let's just go ahead and add together line 2 and line 3, and that'll give us a new equation of 7x, y's are gone, minus 2z is equal to negative 5. Now I want to find another combination to eliminate my y's and add together two lines so that I can have just a system with an x and a z in it. So I'll have two equations, two variables, two equal signs. I can solve for the one variable from there. It's very similar to what we learned in Algebra 2. So what I'm going to do is I'm going to take my top line, I'm going to multiply it by 2. That's going to give me 4x plus 2y minus 6z is equal to negative 6. And I'm going to add it to my second line. I'm just going to rewrite it. 3x minus 2y plus 4z is equal to 2. If we add those together, that gives us 7x, y's are gone, minus 2z is equal to negative 4. Now, I can put that over here, organize it underneath my first new equation. And we can pick a variable to try and eliminate. Let's just go ahead and multiply our bottom line by negative 1. So my top line will stay the same. The bottom line will become negative 7x plus 2z is equal to 4. When I go to add them together, my x's cancel out. Sorry, I mistyped. My z's cancel out, and I end up with 0 equals negative 1. That is never going to be a true statement. 0 is never going to be equal to negative 1. We have a contradiction, therefore an inconsistent system and no solutions. There's 0 solutions. Okay, so let's do a couple more examples here, and let's find out how to solve a dependent system. Now we see here that we have 3 variables we're trying to solve for, but only 2 equal signs. We automatically know we're not going to get an ordered triple. It's impossible for 2 planes to intersect at only one point. They're either never going to intersect or they're going to intersect and form a line that is dependent on itself. So let's find a way to solve for a variable. So let's go ahead and eliminate our z's. It's very convenient. We have a positive z and a negative z. Let's just add our equations together. You end up with 3x minus 3y equals 3. Okay, well, they all have the same coefficient. I'm just going to go ahead and reduce this by 3. So x minus y equals 1. Okay, we just divided everything by 3. So we can tell right now x is equal to y plus 1. The value of x is dependent on the value of y. So let's take this value right here for x and let's just plug it back into another equation. It doesn't matter which one we choose. I'm going to choose the second one. Okay, so 2 times x, which happens to be y plus 1, minus y minus z equals 1. So let's do some distributing. 2y plus 2 minus y minus z equals 1. 2y minus y is y plus 2 minus z is equal to 1. Now, since our x coordinate or our x value is dependent on y, I'm going to solve for z dependent on y. I'm going to move my z over to the right side. So z, and now I'm going to move my 1 over to the other side. Z is equal to y plus 1 as well. So our answer is the ordered triple with an x-coordinate, a y-coordinate, and a z-coordinate. Now, if we recall, our x-coordinate is dependent on y, our z-coordinate is dependent on y, so we're going to let y be our parameter. Therefore, z is whatever the parameter is plus 1, and x is whatever the parameter is plus 1, calling parameter p. Let's go ahead and jump down and do one more quick example here. 3x minus 2y plus z is equal to -1. We've got another 3-variable, 3-equation system, which is great, but that third line has no z variable in it, okay? Which is going to actually benefit us quite well, because if I eliminate the z's by adding together the first two lines, I'll now have another equation with no z variable in it. So let's go ahead and add together the top two. That'll give us 5x minus y is equal to 4. And the second equation is 10x minus 2y is equal to 8. Now, we could do this the same way we just did this one up here. Will be perfectly fine, or even the same way we did the equation before that. But it doesn't take much cleverness to realize that 5x minus y equals 4 is simply scaled down by a factor of 1/2, the same plane as 10x minus 2y is equal to 8. They are exactly the same plane, okay? So we know they're going to overlap, all right? Which means that while it looks like we have 3 planes, we only have 2 planes. 2 planes are this one and some variation of 5x minus y equals 4, or 10x minus 2y is equal to 8. Okay, so let's go ahead and write it out. 3x minus 2y plus z is equal to -1. 5x minus y is equal to 4. 10x minus 2y is equal to 8. Essentially, this is what we have. If we were to eliminate a variable, x, y, doesn't matter, they would eliminate themselves. Thus giving us the situation where we have 3x minus 2y plus z is equal to -1. I'm going to choose to keep the lower coefficient plane just because it's easier to work with. You can see real quick that we have 2 planes. Well, now we have to solve exactly the same way we solved it here. Okay, we're going to have dependence. So let's pick a variable and go ahead and solve for it. If we look right here, we can see right away this is a really easy equation to solve for y. If 5x minus y equals 4, that means y equals 5x minus 4. Just moving my 4 over and my y over. Really simple. Okay, so if y equals 5x minus 4, all I got to do is plug that back in now into my top equation. 3x minus 2 times 5x minus 4 plus z is equal to -1. I can already tell that x is going to be my parameter, so I want to solve for z in terms of x. 3x minus 10x plus 8 plus z is equal to -1. That's going to be a -7x right there. Let's add it over. This is an 8. Let's subtract it over. So our y is equal to 5x minus 4. Our zx is equal to 7x minus 9. X is our parameter. Y is 5 times the parameter minus 4. And z is 7 times the parameter minus 9. The last equation we might save for class. We might go over it at a different time. But thank you very much, and I look forward to working with you in class.